Chapter 7, Series Parallel Circuits. In this presentation, we're going to look at combination circuits, ones that involved series connections and parallel connections. So when we look at analyzing these circuits and understanding these circuits, we simply have to look at the series connected elements as elements that have the same current flowing through them and divide voltage. And when it comes to the parallel portions, they have the same voltage and divide current. And when we come up with our opposition equations to determine total opposition, we have to apply the parallel resistance equations to the parallel components and the series resistance equations to the series. So we just combine what we've learned for each circuit example, either series or parallel, in one circuit. So it says a branch is any part of a circuit that can be simplified as having two terminals. So if we think of our parallel circuit, the last circuit examples we've studied, each and every branch shared the same two terminals of the source. So every circuit that connected between those two terminals was a branch or a parallel branch. The components between these terminals may be any combination of resistors, sources, or other elements. So you've got a branch, you can have a source and any load in that branch. Many complex circuits may be separated into a combination of both. Other circuits consist of combinations which are neither series nor parallel. And an example of this is something called a bridge. Now, a bridge requires special theorems and formulas to determine values of current and voltage and so on. Things like superposition theorem. And this is something that we don't look at in this course. You'll look at that more in your next semester electrical course. But for us, we can simply know that for the purpose of this course, we'll only be looking at a series connection or a parallel connection or both. So let's take a look at this example. In this example, we're not considering the connection of a source. We're just looking at the load components that make up the circuit configuration and what becomes the configuration that gives us our total opposition in our circuit. And if we look here, we can see that we would describe this circuit as R1 is in series with the parallel combination of R2, 3, and 4, while in series with R5. So if we were to look at drawing some true statements from this example, we can certainly say that if we have current flowing here, I, and we call that I total because it's the current leaving the source, we know that we are going to have I total returning to the source as the same amount. And we can say that from what we can see here, that no doubt that IR1 equals IR5 equals I total. Okay, that's a series property that we are applying to this circuit and coming up with that true statement based on what we know about series. Likewise, then, if we look at the parallel connections here, we could say that VR2 equals VR3 equals VR4, being that that is a principle applied to parallel circuits. And so further to that, we can address the voltage division in this whole circuit. And we could say that if we applied an E total to where we have our total terminals here, E total would have to equal VR1 plus VR2 plus VR5. Now realize that because of this statement that we've made here, we could substitute VR3 or VR4 for this term VR2 there because they're all equal. Okay, so it means a few things. If we have voltage and current, or if we have voltage and resistance of R1, we can determine current. And as a result, that means that we're going to have this current as well. If we can calculate the voltage here as a result of having the voltage and the resistance to give us current, that means we can use the current that we just calculated to determine the voltage of VR5 and so on. And so that's the process we go through to determine unknown values when we have a combination circuit like this. But it really comes down to applying the truths and the properties that we know from understanding series and parallel connections. So here we have another example, and here is where we would say that R1 is in parallel with the branch that has R2 in series with the R3, R4 parallel connection. So when we're looking at this, we can certainly say true statements like VR3 equals VR4. We can say that the current I total, so we're going to have I total here, if we call this I1 and we call this I2, we can say I total equals I1 plus I2. We can further say that the current division here, being called I2, would further say that I2 is equal to, we'll call this I3 and I4. I2 is equal to I3 plus I4. This is really the basis to understanding how we're going to analyze this circuit and calculate unknown values. Further, if we look at the E total value that would be connected to this circuit, E total would have to equal VR1. Notice how R1 is right across the two terminals of the source. Well, further, the last branch is right across the two terminals of the source too, and we have voltage division in that last branch. That voltage division is represented by VR2 plus VR3. So we could say VR2 plus VR3. So having source voltage, we can say what VR1 is, calculate its current, that would give us I1. We could determine what our voltage, individual voltage is of our VR2 and VR3 value based on having the current in that last branch, and knowing from subtraction that that current I2 is going to equal I total minus I1. Okay. Yeah, and then don't forget that this VR2 plus VR3, because VR4 is the same value of which we indicated here, you could substitute that for VR2 plus VR4. It's the same value. Actually, I just wanted to come back to this slide because I want to practice doing the opposition equation. So for the opposition equation, we're going to write an equation that's indicating the total opposition from the circuit, and it comes from the circuit diagram, and it means that from this equation we could actually draw the circuit as well. So if we're looking at oops, just a second. Okay, if we're starting by looking at the branch farthest from the source, the first thing we have to do in our equation is to take this parallel connection of R3 and R4 and pack it up and put it in our equation, right? So see how I've put that, what's inside the dotted line, in our equation, packed it up by using parentheses and indicated that needs to be calculated first before we can consider its series connection to R2. So now we have series current being delivered to this parallel network by R2, and so we have to add it to the equation, and that of course would be what we have summarized as this branch and packed it up and put it in our equation. So that all has to be calculated and determined first. So it's all packed up now, and we have to consider its parallel connection to R1. So what would be the process of calculating this? Well, because you've got only two resistors in parallel, product over sum on this part, so that would be R3 times R4 over R3 plus R4. You've come up with that result. You add R3 to it, right? After you've come up with that result, then you can use that times R1 over that same value. So I'm just going to say this comes down here and it's added to R1. So that becomes your product over sum, right? So that means that result is added to R1 to give you product over sum, and that's going to give you your calculation for total opposition. So the rules for analyzing series and parallel circuits still apply. The same current flows through all series elements. The same voltage is across parallel elements. KVL and KCL apply for all circuits. Remember, KCL is for series and KCL is for parallel. Analysis of series parallel circuits. Redraw all these complicated circuits, and we came up with our rules, right? Sources on the left vertically, loads on the right vertically, and label all nodes. Nodes are points of current division. If they haven't been already labeled or given names, give them names before you do a redraw. So assign names to nodes before redraw. So as an example, just simply A, B, C, D. If they already have names, use those names. If there's nodes that are missing names, add names. Okay, develop a strategy. It's best to begin the analysis with the components most distant from the source. So remember I talked about that in a lab. I said the textbook suggests in your analysis and essentially in determining your R total equation, start from the farthest branch from the source and work your way back to the source. So that would mean start at the rightmost branch and work your way back till you reach the source on the left. And it says simplify recognizable combinations of components. So when we do something like this, and we have these two resistors in parallel, we can simplify those as an understanding that R equivalent, or the equivalent resistance of those two in parallel, is simply a series connected component, right? So that means R1 plus R equivalent plus R3. All right. So it says next thing to do is determine the equivalent resistance. So we talked about that. We said after we've gone through all of this redrawing and followed the rules that we said, the very next step is to determine R total. Now, notice how this hasn't said determine E total. And I think it should. This is the textbook. But when we have multiple sources, we need to make sure we determine the total motivating force in that circuit if the sources are opposing polarities or have other issues, and we have to take into consideration both the magnitude and polarity. So I'm going to say that above this should just be determine E total. Determine the equivalent resistance solves the total current, so that would be I total equals E total divided by R total. Now you've got the result for total current. Label the polarities of the voltage drops, so label the polarities, right? And of course that means label current direction, because it's going to be the current direction that determines those voltage drop polarities. So that's part of that as well, labeling the current direction. And then it says calculate how currents and voltages divide or split between elements in a circuit. And verify your answer by taking a different approach. So it means that when you're done, you can go about different means of verification to make sure you have the right results. So let's take this for example where we have some numbers. So we have a series parallel circuit here. We can certainly draw some truths here, and one of them being that IR1 equals I total. We can say that VR2 equals VR3 because of that parallel connection. We can say that E total will equal VR1 plus VR2 or VR1 plus VR3. Okay, you get the idea. That's where we're going to start this analysis. Notice how we don't need to redraw this circuit. The source is on the left and it's vertically aligned. The loads are on the right and vertically aligned. We can use the voltage divider rule to determine values of VA, VB, VC, and so on. So when I say VA, VB, and VC, sorry, that's a single subscript indicating reference to ground, and there is no ground in this circuit. When I say that, I mean we can determine values of VAB, VBC, VAC, and so on. Okay, so let's take a look at this circuit then, and let's start by determining what our R total expression is, because that's going to be our next step. It's already redrawn in the manner of which we would use to analyze it. So that being the case, then we can say that our R total equation is R2 in parallel with R3 then added to R1. Notice how we packed up that R2, R3 connection, and then we're going to add it to R1. So if we start with product over sum then for this part, that's going to be 10 times 40 over 50, right? So that's 400 over 50. That would be 8 k ohms. Now that we have a result of 8 k ohms, we simply have to add that to our 12 k ohms in order to give us 20 k ohms of total resistance, right? So now what do we do? Well, we can move to our total current, right? So that's the process. That's the next step. I total equals 48 volts divided by 20 k ohms and gives you a result. Okay, so 48 volts divided by 20 k ohms is equal to 2.4 milliamps. So we're going to indicate that our total here is 2.4 milliamps. We've calculated our total current. Now we can determine our voltage division based on IR values. And the simplest way to go about that is to determine the VR1 value that we see here is the one that's conducting total current, and then you can subtract that from the applied voltage. That's using Kirchhoff's voltage law. So let's take a look here and let's calculate that value. So that means that VR1 is going to equal 12K times 2.4 Okay, so now we have 28.8 volts. And so now, if we're looking at our VR2 equaling VR3 value, that can be determined simply by subtracting our 28.8 volts from our 48 volt source. So that's 48 minus 28.8 gives us 19.2 volts. Then from there, in order to determine our current division, we know we have 2.4 milliamps entering this node. We have I2 and I3 exiting. So I2 then is simply going to be determined by Ohm's law. We know we have 19.2 volts here. So I2 is going to be 19.2 volts divided by 10K. So what is that? 1.92 milliamps. We could use subtraction to determine our I3 value, because I3 would equal I total minus I2. So that means you could take 2.4 milliamps and subtract 1.92, and you would get 480 microamps. Right. Now, if we want to double check, remember that's what it said in the last part of the other slide there, is use other methods to verify. We determine that current by subtraction, but there's no doubt we can determine it using Ohm's law, right? So remember, we've got VI3 will equal VR3 divided by R3. So remember, VR3 is 19.2 volts divided by 40K. We should get the same result, right? 19.2 divided by 40 exponent 3 gives us 480 microamps. So we're just confirming using other methods. Okay, so that's a pretty simple example, but it gives you the processes that we would do to come up with the unknown values. From there you can go about determining powers if you want, because we have voltage and current for each component. All right, so here's an example of a series parallel circuit, one where we need to redraw it. So when we look at this example, we do not have vertically aligned loads, and we do not have loads on the right and source on the left. So we're going to redraw that circuit for our first for the first step of our circuit analysis. So what's our process for redrawing? Well, I always say take your first path for current to flow and label all loads within the path for current. So that means you'd be labeling R2 and R3, but you'd also be labeling this point B. Then you need to move on to your next branch for current to flow and follow it back to this point here where you're returning to the source. Notice how you've got two unlabeled current division nodes here. So now I would say that you're labeling those as C and D before you get started into your redraw. So in your next tracing of the next branch, you're going to have R1, R4. You're going to have to make sure you include point A, and you're also going to have to include your current division nodes labeled. Okay, here's where we have the redrawn circuit. The only thing that hasn't been included from the textbook here is labeling these two current division nodes, which I talked about from our original diagram. So that would make this current division node C, and this down here current division node D. So we would make sure that we labeled that on our redrawn circuit the same names that we gave them in our original diagram. So notice how this has all been redrawn. We've got our loads aligned vertically on the right and our source over to the left here. And this is the equivalent redrawn circuit. So it becomes a parallel circuit made up of two series connections, right? So now if we want to move forward to determining our R total, we have to come up with our expression, right? So textbook suggests starting at the farthest branch. The farthest branch is a, sorry, had a little bit of glitch in the presentation there. R1 plus R4 is our series branch for our last branch. We have to pack that up. That's in parallel with R2 plus R3, which has to be packed up as opposition for that branch, and the two branches are in parallel. So now we just go about determining the values in each branch by adding them up. So the first branch we see here is going to be 100 plus 300, so that's going to be 400 ohms there. The next branch is going to be 50 plus 200 to give us 250 ohms there. That's in parallel. So now we can go about using product over sum. So our total is going to equal 400 times 250 over 400 plus 250. Times 250 divided by 400 plus 250. If I got this entered in my calculator correctly, then that should be 153.8 ohms. So we're going to call that, for purposes of today's demonstration, 154 ohms. All right. So now from there, we can determine our current division, and ultimately what we're looking for here is a value of voltage, VAB. And if we're looking for just that voltage, I would say there's probably an easier way to go about this, and you could just use voltage divider on the two branches to determine a value of voltage at point B and a value of voltage at point A with respect to point D. So that's, if all we were looking for was VAB, that would probably be the most efficient way of doing so. And of course it says you can use the voltage divider rule on each branch to do that. But let's say we're going through the whole process of currents and so on. Well, we could determine our I total value here based on our applied voltage divided by our total value. So I total then would equal 40 volts divided by 154 ohms. To give you 259 milliamps, 259.74. We'll go 260 milliamps. I'm doing some rounding off here to speed up the presentation. 260 milliamps is our current entering. That means we've got current exiting here and exiting here. And what's going to determine those branch currents? Well, simple Ohm's law. Remember, we have 250 ohms of resistance here that's connected right across that 40 volts. So that means that I1 will equal 40 volts divided by 250 ohms. I2 will equal 40 volts. It's the same voltage divided by 400 ohms. So the first one is 160 milliamps. The second one is 100 milliamps. You can see the two of them add together to give you 260, knowing that that's confirming Kirchhoff's current law. And now, knowing our currents for each branch, we can determine the value of VAB here. So let's do that. I'm just going to erase this stuff so that we can remember our values, and we'll label them next in here. So remember, what was our current through here? We had 160 milliamps. Current this direction was 100 milliamps, and the current entering here, you know, was 260 milliamps. So that being the case, we know we can determine this voltage here of R3 and this voltage here of R4. And then VAB is just the difference of voltage of those 2 points. So we'll use this point here as essentially our reference, and we'll come up with VR3 equals 160 milliamps times 200 ohms. Over here, VR4 is 100 milliamps times 300 ohms, right? So 160 milliamps times 200 ohms is 32 volts. So that means we have a 32 volt value for VR3, and the polarity of that drop is plus on the top, minus on the bottom. It's going to be the same polarity here when it comes to VR4. So we're going to calculate VR4. That's going to be 100 milliamps times 300 ohms, which is going to give you 30 volts. Okay, so in order to come up with a VAB value, it's the difference between 2 point voltages. And if we look at using the same point here of reference, we've got a point B that is 32 volts positive of that point. We have to take the same point, which is over here. It's the same point. There's no voltage dropping resistance or opposition between those 2 points. So if I call that point A, I can call this point A as well. Oh, sorry, I shouldn't call it A. We already have A in this circuit. So let's say we were just going to call this X. This would be called X as well. It's the same point. If we look at that same point X and we look at point A relative to the same point of which we determined that was 32 volts for point B, we can see that point A is 30 volts. So now we're looking at a value of VAB. So what's our reference? That means our reference is point B. So we're starting at point B and we're comparing it to point A. Notice how point A is 30 volts negative of point B. 30 volts with respect to plus 32 volts is a minus 2 volt potential. So that means our VAB value would equal minus 2 volts. All right, so here's an example of where we need to redraw this circuit, of course, and source on the left, loads vertically on the right, labeling all current division and points. Now, notice how we have a current division node right here. That current division node is the same point as D. You see that? It's the same point. So realize that we may find it helpful when points are kind of separated or spread out like this, understanding they are the same point. Label this D. We're going to label that D before we start our redraw. Okay, so I brought the original diagram into this workspace. Remember, we said this was the same point D here, as what we saw here. So we're going to label that D. So the way I'm going to start off with this is if we look at the source voltage 45 volts here in this circuit, we're going to show that as on the left and vertically aligned. But notice how we have 2 points that are labeled A and D now. The point A is on the positive terminal of the source, and point D is on the negative. So when I go to draw this, I can make enough room to have lots of components shown on this circuit, but I can say that on the positive side, I can label this point A, and on the negative side, this can be labeled D. That's clearly what we see here. Negative terminal of the source is labeled D, positive terminal is labeled A. It means that all of my circuitry now is going to be connected to those 2 terminals of the source. So I'm going to start with my first path for current flow. Notice how this one's labeled I1. So I'm going to start by following this path and returning to the source. And how does that, when we follow that path, what are the loads that we flow through to get there? Well, I'm just going to extend this current division node A over here, and I'm going to first put in my R3 value. So this is R3, and it's 3k ohm, right? So we have 3k ohm. Notice how as soon as we exit R3, we have a current division node we're going to label B. Okay, so then we carry on, and we have R2. R2's value is 4k. And once we get through R2, we have another point of which is labeled C. Okay, now I'm carrying on. I have R1, and it's 6k. Notice how that brings us all the way back to point D. So that means that brings us all the way back to the negative terminal of our supply. Okay, and this is 45 volts for our E source value. All right, now what we can do is we can move to the next branch, which is called I2, and follow it through until it returns to the source. So if we look, we've got current common with the terminal A. It goes through this 3K, so we don't need to trace another path. But as soon as we get to this point, we have current division. This is where we need to pick up our current flow. Okay, so picking up our current flow from node B. So this would be where I2 takes off. We have R4 as our load, and it is a 15k ohm load. And where does it come around to? It comes around to returning to point D. So that's simply down here to the negative terminal of our source. Okay. Now we've got a complete diagram. We can go through and check to make sure every single current node is labeled. We've got A, B, C, and D. The original diagram has A, B, C, and D. We've got every load labeled, R1, R2, R3, and R4. And we have the source to the left and everything aligned vertically. So that means we're good to go now. And so what's our next part of our process? Determining our total value. So we're going to say that our total then, starting from the branch farthest away from the source, we're going to say that we're going to pack up R4 in parallel with the series combination R1 plus R2. Okay, now that all has to be packed up and determined. has a value inside this box here before it's added to R3. Okay, so let's go about determining the total opposition here then. So we're just plugging the values in. So R4 was 15K. That's in parallel with an R1 plus an R2, which is 6 plus 4. So that's 10K. And what we'll do is we'll determine that product over sum value before we add it to our 3K, because remember, we're adding it to the R3 value, right? So we're going to come up with this first. So we're going to go 150 over 25. Answer will be in K. So that's 6K. So we have 6K as the result there. Now, after determining that, we're adding it to our 3K to give us a total of 9K ohms. So we know we have 9K ohms of opposition. Where do we go next? So what are we determining next? I total is equal to E total divided by R total. That's going to be 45 volts divided by 9K ohms. So answer is going to be in, when you have whole units of volts divided by K ohms, answer is going to be in milliamps. So that's going to give us 5 milliamps of total current. Therefore, that means we know we have 5 milliamps of current flowing here. We can see that R3 is conducting that 5 milliamps. And so now we can calculate our VR3 value. So VR3 is going to equal 5 milliamps times 3K ohms. So the K and the milliamps cancel out, and you've got 15 volts. So put that right in your diagram of 15 volts as your voltage value, and know that based on voltage division up for this series connection, that the value of 15 volts subtracted from 45 is going to tell you the voltage across this network, right? So that means we can say that VR4, which is the only resistor in that network that is on its own, we can say VR4 is going to equal E source minus VR3. So that's going to be 45 volts minus 15 volts equaling 30 volts. So we can say that our value of voltage here is 30 volts. So now we can calculate currents, can't we? 30 volts divided by 15K is 2 milliamps of current in this branch. I'm kind of speeding things up a bit here. 2 milliamps here. That means if we have 5 entering and 2 exiting, that means there's got to be 3 milliamps here. Based on 3 milliamps here, we know there's 6K times 3 milliamps is 18 volts. We've got 3K times, 3 milliamps times 4K. We know that's got to be 12 volts. Notice how the 18 plus the 12 equals the 30. The 18 plus the 12 plus the 15 equals the 45. The 30 plus the 15 equals the 45. Everything's working out properly for current division and voltage division. Now we've got every value that we need, and we can determine all single subscript, double subscript values. Remember, the polarity of voltages are going to be plus minus, plus minus, plus minus. So you can calculate any value you could possibly imagine. Let's say we wanted to come up with a value of VBC here. VBC. We look at point B and we look at point C. C is the reference. So that means we have a plus 12 volt value for VBC. bridge circuit. This is actually not what's technically a bridge circuit. This is simply a series parallel circuit with two parallel connected series branches. The textbook's calling it a bridge circuit, but technically it's not a bridge circuit until you put a resistance right here. Once we have a resistance right here in this circuit, this bridge resistor, this becomes now a bridge, and what it means is you need to use superposition theorem and so on in order to determine the current flows and the voltage drops, because it's not a purely series and parallel connection. And like I said, we don't study those in this course, so you don't need to worry about that. But for whatever reason, the textbook is calling this a bridge circuit, but it's not technically a bridge. So I just wanted to point that out. So remember, we have no resistor there, so it's just a series parallel circuit. Now, the first thing we want to do, as always, is redraw a circuit that's odd for us. So when we say odd, you can see that the source is to the left, the loads are to the right, but they haven't been aligned vertically, right? So we always suggest doing that in order to simplify your understanding of the circuit based on that common standard of redrawing circuits. So if we look at this next slide, that's what's being done here, right? We've taken our loads, drawn them vertically, and we have the same manner that we did in the previous slide, or we have the same circuit in the previous slide. So let's just say I was to label current division node A. Again, I'm using A, which I shouldn't because we have them there. Current division node C and D here. In this diagram, this would be current division nodes C and D. So we want to make sure that when we redraw, we include those current division nodes. It says use the voltage divider rule to determine VA and VB. Now when we're talking about VA and VB here, when it comes to these two voltages, remember this is all with respect to ground, right? So I don't like the textbooks using VA and VB without including ground in the circuit. VA and VB have no meaning without including ground in the circuit. So notice how here I've added ground to actually give this meaning, right? So now VA and VB have meaning. So let's go about doing this. Now that we've assigned ground to that point, we can determine two single subscript values to determine a double subscript. So let's start by doing that in this example. So the first thing we'll figure out is VA. So VA will be found by voltage divider rule with 200 ohms here and 50 ohms here. That's going to be 200 over 250 as the total resistance for that branch multiplied by 10 volts. For VB then, we're going to have 15K and 5K. So we have 15K over 20K as the total value of resistance in that branch times 10 volts. So that's going to be 8 volts for VA. For VB, we're going to have 7.5 volts. If we look at the voltage drop polarities, they're both plus. And so now if we want to know a VAB value, we know that that's determined by VA minus VB, right? VA is equal to 8 volts plus 8 volts. Now we're subtracting plus 7.5 volts. The result is plus 0.5 volts. And that's what we see here. Now it changes things up and it says suppose that Rx, that is the value here, is equal to 0, right? Well, that being equal to 0 now, we know that there's no potential difference here. So this voltage, no doubt, VB, is going to be 0 volts, right? Whatever current is in that branch, and matter of fact, we know the current will be, there's only 5K ohms in that branch now because we've got 5K plus 0 ohms. So that branch current, I2, will equal 10 volts divided by 5K, which will equal 2 milliamps. So now 2 milliamps times 5K is a total of 10 volts across that device, making it 0 volts right here. So we can no doubt say that VB is equal to 0 volts. Now let's figure out VA. Well, VA hasn't changed, has it? Previously, we determined that VA is 8 volts. Based on the fact that VA hasn't changed because there's been no change in the resistance of that branch, we can say that VAB is equal to VA minus VB. VA is plus 8 volts minus 0 volts is obviously going to be plus 8 volts. And that's what we see here. If we look at the VR2 value we talked about, that is confirmed here from what we calculated as 2 milliamps times 5K ohms to give us 10 volts. So the value of voltage here was 10 volts. So if we have a 10 volt drop there, that means on this side we have 0 and on this side we have plus 10 volts. So now we look at the opposite. What if this is infinite ohms of resistance? Well, if we have infinite ohms of resistance here, that's an open circuit, right? So based on the fact that we have an open circuit, that means that all of the source voltage will appear here now. So now this will be 10 volts, and this will be 0 volts, the opposite of what we had before. So that being the case, then we know that VB now is equal to 10 volts. VA hasn't changed, so VA is equal to plus 8 volts. So now we simply come up with VA minus VB to give us VAB. That's going to be VA of plus 8 volts minus a plus 10 volts is going to be the result of minus 2 volts. Which is what we see here. So what if we wanted to find VR1? Well, VR1 is just going to be a subtraction, isn't it? So we can say that VR1 equals E source minus VR3, because it's a voltage divider. And VR3 was essentially this VA value of 8 volts. This was 8 volts, right? So that's going to be 10 volts minus 8 volts to give you 2 volts. So we can say that the voltage across this R1 is 2 volts. Okay, so if we look here, we can look at this as a voltage divider, but a variable voltage divider, and it's just looking at that potentiometer example like we used in the E-lab, except it's wired differently in this case. All 3 terminals are connected. So that means you have a terminal connection on the top now, and on the bottom, and a terminal on the what's called the wiper that can be adjusted up and down. What it means is that your value of resistance between these 2 points can be changed, and these 2 points can be changed. So when you're looking at determining the value of potential VBC here, it's all relative to the amount of resistance that you see between these 2 points, right? Because this is your point of reference, VC is your point of reference. The amount of VBC is going to be totally dependent on the percentage of this 50 k ohm resistor that you are adjusting it to. So let me give you an example. Let's say it was 100%. If it was 100%, R2 would be 50 k ohms. That means you'd have 50 k ohms in series with 50 k ohms. It's a voltage divider. Each one would be dropping half of the voltage because it's equal resistance connected in series. And no doubt with this at 100%, you would have 60 volts here. What about when it's at 0%? That means there's no resistance whatsoever between this point and point C down here. So as a result, you would develop 0 volts of voltage drop. So when it's at 0%, VBC would equal 0 volts. Now what we're doing is we're bringing in a load resistor in parallel with this amount. So I'm going to leave you to experiment with this and do calculations, but I'm just going to say, let's suppose this was at 50%. So if it's at 50%, remember that's a 50 k ohm potentiometer. So that means you would have 25 k ohms on this side, 25 k ohms on this side, and this guy is 50 k ohms. So how do we interpret that then? Well, what it would actually look like is a circuit like this. 50k as R1. Then you'd have 25k in series with that. Then you'd have a current division node and have 50k over here as R load. And then you'd have the remainder of the potentiometer's resistance of 25k here, and that would become your circuit. This would be your point C. This would be your point B. So how would you calculate this? Well, you'd have to come up with your R total equation and determine your currents and your voltage drops in order to determine the result here. So you could use voltage divider rule here, but you'd have to use voltage divider rule after determining the equivalent resistance that's here. So this would be 25k in parallel with 50k, which we can use product over sum. So that would be 25k times 50k over 25k plus 50k, and that would give you a result of R equivalent. So let's go with that. We'll figure out R equivalent. That's 25 times 50 divided by 75 equals 16.67 k ohms. Okay, now this VBC, you can see, is the voltage across R equivalent. So another way to say this is, from our diagram, our R equivalent here is going to be equal to VRE is going to equal VBC. So knowing that, then we could use voltage divider rule here. And what it means is you've got the equivalent total resistance of 50k in series with 25k in series with R equivalent equaling 16.67k. So this is all a series connection, so you can come up with a total resistance value, R total. So our total is going to be determined by 50 plus 25 plus 16.67. That gives you a total of 91.67 k ohms. Okay, so that's our total resistance. Now we want to know, because this is point B and this is point C, and we're trying to determine VBC, it's a simple calculation of voltage divider rule. So we can say that VBC will equal R equivalent over R total times E source. So in this case that would be 16, whoops, that would be 16.67 over 91.67 times 120 volts. So 16.67 divided by 91.67 multiplied by 120. That's going to give you 21.82 volts. That's going to be your VBC value when you have 50 that's going to be your VBC value when you have the potentiometer set at 50%. Okay, so that's it for that presentation. You need to go to your textbook to chapter 7 now and practice your redrawing of circuits, your circuit analysis, your evaluation of parallel connections and their same voltage but current division, your series connections with the same current and voltage division, and combine all of that knowledge into one circuit and analyze it following the steps. So don't forget, follow all the steps, and you'll make something that's difficult much simpler, and that's the idea until we get some experience. All right, so good luck.